this should be, get my sound reflector up here, Organic27DBlake. Between these, I think this will be the last video for the redox section. So this should probably get us up to sometime on Wednesday. And I wanted to point out a few things before I continued, because I've missed a few things. If you go all the way back to this flip chart, page 27, make sure you are familiar with the oxidation number rules from page 686. I mean, for 95% of the things, you don't have to know most of the rules. You know, the first rule, make sure an uncombined element is 0. Anything that's usually an ion, like an alkali metal, make it equal to the charge. Oxygen's usually -2, and hydrogen is usually +1. Where that's at in here, I don't know. And this rules will look a little bit different book to book. Nobody's going to use exactly the same set of rules because they don't want a copyright infringement lawsuit. But basically, if you know hydrogen's +1, oxygen's -2, anything that would usually be an ion, like in the halogens, chlorine, bromine, anything that would be an alkali metal, like lithium, sodium, potassium, those are the same as the charge. That's 90% of it. In fact, while I'm on this topic, let me drag you through the mud here. Well, here, I forgot. This table that we use all the time, I mean, this is going to tell you the oxidation number most of the time. You know, these are usually going to be +1, these are usually going to be +2, these are usually going to be +3, these are usually going to be -1, these are usually going to be -2. Let me do this. Maybe you didn't pick up on the cursor movement. These are usually +1 oxidation. These are usually +2. These are usually -1. These are usually -2 oxidation. So, I mean, those are pretty much always the case. Not always, but most of the time. So hydrogen's 1 because these things are +1. Oxygen's -2 because everything in that family is -2. Because oxygen never anything else? Yeah, but those are exceptions that we don't need to really worry about too much for our purposes. So there's the oxidation number rules. So be familiar with them. Know where to find them in the book. They're on page 686. Then, I probably blasted past this mentioning it, but there is on page 694, table 6, in the general chemistry book, this table that tells the half reaction method. Now this definitely is different from what you'd see in other books. Just, you know, if you take another chemistry course, they're going to have a little bit different approach. But you're still doing the same things. It's just they got to make sure they're not sued by the lawyers. Now, when I wrote this, in the old book I had a different way it was a little bit set up, so I deleted all that and did these this way. And I've been going through these 6 steps without specifically saying, hey, you do this, then you do this, then you do this, then you do this. So that's where it comes from. So you may want to refer to this table. And yes, at some point we're going to have a quiz in week 27, which will be next week for me and the week you're in for you. And on that quiz, you can use this. And on that quiz, you can use the their general chemistry book. So you probably need to know where to find these pages. Look them up and, you know, put a, what do you call that? Post-it note in there or something so you can find those pages quick and you can use that chapter. You can use that reference materials. At least those pages. So we left off, okay, I want to go back to this. The last one I did on the last video. I pointed out that I used potassium dichromate and potassium iodide because I wanted to eliminate the possibility of any interference by using, let's say, ammonium dichromate and potassium iodide, and those ions are different, and the ammonium ion's off doing something different, the water chemistry doing its own redox reaction, creating a nasty surprise. So I used something that I knew was compatible, potassium with potassium. But what I forgot to mention is I intentionally chose hydrochloric acid because I didn't want to use nitric acid. And as I mentioned in video B, yeah, you can get a nasty surprise with hydrochloric acid, but that's not something I would ordinarily expect to be a high likelihood. If you use nitric acid, you can expect to be surprised because that nitrogen ion in that nitric acid is going to take every opportunity it can to change oxidation number and do a redox reaction and pump out nitrogen dioxide or something like that. It's not as likely with chlorine ion. So I intentionally chose this one for that reason. Okay, I want to check my board over here because I wrote some notes for myself to mention some things. Okay, I think we're good to go. Move forward. I think we did the one, we're on page 71. So this is where we ended up. And I've been quite a bit under the weather for the last several days, so I can't get my voice volume up, so that's, I know, a problem for you listening, but I'll do the best I can. Try to stay a little closer to the microphone today. So let's go on. I intentionally jumped from 25 back to 24 because if you look at what was going on, we did the half reaction method so that we could work in acid environments and base environments or neutral environments, and it's a little harder to do the half reaction method, but it works in all the scenarios. All the ones I did there yesterday were in an acid environment, and we were finishing near the end by balancing using hydrogen ions and water. And I wanted to end on that because that seems to be a little more common. So I went out of order on number 24 and 25 so we could do the one with hydroxide ions and water and then go back and end on ones with acids. That's my thought process. I don't know, maybe it doesn't work for you. So we did number 25 in basic solution so that I could end with one that was in acidic solution. And these are all assigned. I haven't said that yet in the videos, but you'll get that message from me, or you have got that message from me by now. So we have another reaction they've given us in that problem where they have taken the spectator ions out already. They're not there, you don't have to do it. So the first step of that 6 back on that page of that table that I told you to take a look at is to write the unbalanced reaction, so there's no coefficients. It's the net ionic equation, so it just shows the things that are changing. No spectator ions. So we have a manganese 2 ion, bismuthate ion, permanganate ion, and a bismuth 2 ion. So now we're going to split those apart into an oxidation reaction and a reduction. So we're going to have these two in an equation and these two in an equation. So if you're following that table, second part, write separate incomplete equations for the oxidation and reduction half reactions, including oxidation numbers. So we've got the bismuthate ion changing to bismuth ion. We have to add the -1 on the bismuthate ion equals -1. There's 3 oxygen, minus 2, minus 2, minus 2, and something. Well, 5 minus 2 minus 2 minus 2 gives us negative 1. So the oxidation number for bismuth there is plus 5. Here it's plus 2. It has to gain 3 electrons to do that, and it's oxidized. This is an oxidation because this is a reduction. I have this upside down. This is a reduction. Oxidation is losing, reduction is gaining. Hopefully. I have to fix that. Sorry for the time delay, but that's just the way it goes. Once these flip charts are all done and all these things are fixed, when you're long gone. Let's see. Oxidation is losing and reduction is gaining. And I'll switch their positions possibly later. And by the way, if you find a mistake in one of these, point out, hey, back on flip charts such and such, you screwed up. Okay, good. I'm stuck on it. That's not going to offend me. If you let me know I made a mistake. So I think you made a mistake. Well, if you know I made a mistake, just tell me I made a mistake. You don't tell me, you think I made one if you know I did. Okay, well, going on, the next thing is, you balance the atoms in the half reaction. And then the charges. See, don't worry about back here. This is, this is why you want to work a bunch of examples. Don't worry about balancing these electrons and these charges right here. Because they don't right here. I'm going to continue with that. The only thing you're putting the electrons in there right here for is to show really whether they're going in and you're gaining electrons or if you're losing. We don't really care about this number at this point because we haven't balanced the atoms yet. That's what's now. Okay, and then we'll balance the charges. So now, this is an acidic environment. You need to know that because that tells us we can put water in there to balance oxygens and we can put hydrogen ions in to balance hydrogen. So if you got bismuthate ion and you're ending with bismuth 2 ion, we need 3 oxygen over here, so we add 3 water so we can get the oxygen. That means we have 6 hydrogen. So I have to add 6 hydrogen ions over here. And now we can put our electrons in. We're ending up, and you do that by balancing the charges. Okay, we're going to end at 2 positive, and we have 6 positive and a negative. That ends up with 5 positive. So I need 3 more electrons to end up at 2 positives. So 3 negatives, and this negative is 4 negatives. Add that to 6 positives is 2 positive, which is what we have over here. So we can check our electrons. A lot of times your electrons will change at this step. Okay, on the other one, we were taking manganese 2 ion and using it with some other stuff to make a permanganate ion. Well, I have oxygen on this side, and I need 4 oxygen on this side, and the only way I can get it in there is to add 4 water. But when I do that, that gives me 8 hydrogen atoms. So I need 8 hydrogen over here, we'll put them in the form of ions, because that's all we can do in an acidic environment. Then we got to check our charges. I have a 2 positive here. I have an 8 positive here. Knocking 1 off, I'm down to 7 positive. It's still 5 too high, so if I have 5 electrons on there, that'll make the same amount of charge on both sides. You got 8 positive, 5 negative is 3 positive, an additional negative is 2 positive, and this side's 2 positive. Now, we got this far. Remember, you can follow those steps. I'm on the 3rd one. I'll let you use that chapter. I'll let you use that page that has this table on it to go through there. You wouldn't be able to do that in a college class, but we're not in a college class. All right, so anyway. Now we want to do is balance these charges. So if I multiply this whole equation by 3 to get 15 electrons, and this whole equation by 5 to get 15 electrons, then we can add our equations. And by the way, we're going to have water on both sides. Some of that's just going to cancel. And we're going to have hydrogen ions on both sides, and some of that's going to cancel. So let's take a look at the next page. Adjust the coefficients of the number of electrons lost in the oxidation number. Oxidation equals the number of electrons gained in reduction. So I multiplied the whole top equation by, I think, 5, and the whole bottom equation by, I think, by 3. By 15 electrons cancels. Notice I have 12 water and 15. That's going to leave 3 water on this side. I have 30 hydrogen ions and 24 hydrogen ions. That's going to leave 6 hydrogen ions on this side when I add everything. So all this stuff gets added together on the left. All this stuff gets added together on the right. But I went ahead probably and canceled out the hydrogen ions in the water, so I'm left with 6 hydrogen ions and 3. And this is pretty much what we've got. Now I added the half reaction, that canceled electrons, it reduced like terms. We have 30 and 24, 30 on one side, 24 on the other, that gave me 6. I don't remember what it was for water. $15 on this side and 12, that gives me 3 on that side. Next. So you got to know what to do. And if you have the diagram to tell you what to do, it's much easier, I guess. Return the spectator ions if desired. I don't think they gave us any spectator ions in this one. And then you put in your state descriptors. So aqueous, 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 and liquid for the water. Okay, I gotta go in and make a couple changes in there. And now, wherever you're at on this, I don't know if it's Tuesday or Wednesday or what day it is for you, we're gonna go into week 2-7 and back into the book. But when you're in, which would be probably Thursday for gold and probably Tuesday for green, second day, I want to have a little quiz over this redox. If we can't get it that soon for green, then we'll have to push it back, which is okay. Okay, on to next video, will get us into chapter 27, or get us into week 2-7 properly with the book.